Good evening once again. In yesterday's video, we had looked at one problem on work energy theorem. Let me go back to this. Okay, the first video, we had looked at how do you use work energy theorem, conservation of energy, and equations of motion to find out what is the speed of the particle due to free fall when it reaches the ground, right? This one is a very familiar problem. Most of you would have done this. Nothing new. Okay. But while these two were quite new for you, okay, how to do this one? It's quite easier. Then the second one, when a particle moves down an incline, now how do you find out what is the work done by the particle? So here, this is something which you would have solved it. And this is also, okay, I introduced about the concept of using work energy theorem. And here you can solve it by three methods. The first method is by kinematics. Second method is by combining work energy theorem with equations of motion, or combining work energy theorem plus conservation of energy. Okay, you can use any one of them. Then the last method is, let us say you are not a physicist at all. Okay, you still have been given something like this. Okay, and you do not know anything about the physics point of view. So you can also use this way, the vector method. You can use this one here, right? So we have seen all the three methods. All the three methods for the second one. Now let us do one more example. Now here's something new here. Okay. So what is the work done by a particle of mass m kg whose velocity decreases as shown in the graph? There's a VT graph given to you, and we need to find out what is the work done by a particle. Now, towards it, what we need to do? First method. What is the first method? First method is by, guess what will you do? Now you see, potential energy is not known to me. Okay. Let us use kinematics method first. By method of kinematics. The moment a VT graph is given, we always think, okay, the only thing that we can do is we can find out the displacement, we can find out the slope, right? And that is what is required here also, okay, to find out using kinematics. Now work done is given by F into S. That's what we know, okay? We need to get the value of F. Now what is the value of F here? Force. How do I get the value of force? Force is equal to mass into acceleration. Now, how do I get acceleration? Acceleration, I don't know. So what we can do is find out the slope here. Find the slope. What is slope here? Slope is nothing but this value of V divided by this value of T, right? Changes in Y value by changes in X values. So therefore, I can now write this as changes in Y value is V minus 0, V minus 0. Why V minus 0? V minus 0, right? Divided by, what did I do here? I started with initial velocity, final velocity, initial minus final. So initial time is 0 minus final time minus T. Okay, which should now be equal to minus mv divided by t. That's what you should get, right? Okay, and then next is displacement. How do I get displacement? Displacement is nothing but the area under the curve. What is the displacement here? Displacement according to this is nothing but half v into t. That's what we have. Okay, and when I write the work done, I'm going to take the magnitude of this. Okay, and thus I'm going to write W is equal to F is mv divided by t, and this is half v into t. So what happens? This t and this t goes away. Then you get mv into v divided by 2, which should be equal to mv square by 2. Yeah, we have got half work done is equal to half mv square, which is nothing but your kinetic energy. You know, there are some details missing here. The details here are, see, I said initially dot, then suddenly I multiplied. Can I do that? I did it assuming that, okay, so the angle between them is 0. I assumed it. Okay, these details are not given to you. You can do this. Okay, now, first method is done. Let us prove the same equation by using work energy theorem. Now, work energy theorem. Work energy theorem. Now, what do we do here? In work energy theorem, so what does it say? Work done is equal to the difference in the kinetic energies of the particle. Difference in the kinetic energy of the particle. Some students make a mistake saying that, see, the particle is moving like this, it's sliding like this. It is not sliding. Okay, don't consider sliding. I am not describing any particle here. I am just saying the velocity of the particle initially was so much, finally is so much only. Okay, so as a result of it, okay, maybe even if you consider the negative value here, I can also put a negative value here. So I get minus kinetic energy here also. So similarly here also, the final kinetic energy here, when it comes here 0, minus initial kinetic energy was half mv square. So thus I'm getting W is equal to minus half mv square. Right? I forgot to put this. Thus you see, the work done here and work done here is one and the same. Okay. But what is missing here? You do not know how the particle is moving. But of course, here it is being given as a straight line. Now let us say if the graph is not a straight line like this, but instead the graph is a curve like this. Curve like this, and finally it reaches here. This is my initial velocity and it reaches this point. Now what will you do? Now comes the real play. You cannot solve this equation using this method. You can solve, but it becomes very, very difficult for you. Because here one thing that we assumed is acceleration is constant. But here you see, acceleration is constantly changing. Okay, acceleration is no more a constant. You find the slope here is different. And much of the information is not given to you, then the easiest way to solve it is using your work energy theorem. Now let us solve it using work energy theorem. Work energy theorem here is nothing but final velocity, which is 0, minus initial velocity, which is minus half mv square. So finally, this will be your work. Okay, if I take the magnitude of this, so this will be your work. Now, how do we get the same equation using kinematics? If suppose, okay, by some way I'm going to do this. Okay, so in that case, what I need to do is I need to find out the acceleration at this point, at this point, at this point. N number of points I'll find out. Every point I find out. See, at all these points, acceleration is a variable and it is all negative here. But when the line goes like this, acceleration is a positive quantity, and then you see it is varying once again. When it comes here, it's a plateau region, acceleration becomes 0. Once again, it is negative. Now, what we need to do is we need to consider the sum of all these accelerations. Not sum of. We need to consider the sum of all the work done. Okay. So work done in bringing a particle from here to here could be W1. From here to here, W2, W3, W4, W5, W6. Okay, I keep on adding up all this work done. So finally, I will arrive at this equation. Very, very tedious job. But the easiest way is by making use of the work energy theorem. Now, I hope you understood the easiness, or what you call as, okay, the difficulty in solving problems using kinematics as compared to the energy methods. Energy methods are always the easiest way of solving problems. Okay, so towards it, so I hope you have understood this problem clearly. And what is the utility of work energy theorem? With this, let me stop here. And if you have any questions, you can drop it down in my comments box so that I will be happy to answer it. And like, share, and subscribe to my channel for more updates. Thank you, friends, for watching.